Welcome to this specialized mathematics lecture on Introduction to Trigonometry, designed for Class 10 students. The word trigonometry is derived from the Greek words trigon, meaning triangle, and metron, meaning to measure. Historically, this branch of mathematics arose from the practical needs of astronomers, navigators, and land surveyors to calculate distances that could not be measured directly, such as the distance from the Earth to the stars, or the heights of mountains across valleys. Today, trigonometric equations are the silent models running our modern world, structuring everything from GPS flight navigation grids and solar angle coordinates in architectural designs, to wave frequencies in electrical systems and the complex vector graphics coding of digital games. Today, we step into this powerful geometry to master right-angled triangle ratios, prove scale-invariant similarity properties, and derive the core formulas that allow scientists and structural engineers to map and measure our physical universe. Let us establish the exact geometric definitions of trigonometric ratios. Imagine a right-angled triangle, which we will designate as triangle ABC, with the right angle located at vertex B. Let us choose an acute angle at vertex A, which we will represent using the Greek symbol theta. With respect to this angle theta, we can identify three distinct sides. The side opposite to angle theta is the opposite side, representing the vertical perpendicular height. The side adjacent to angle theta is the adjacent side, representing the horizontal base. And the side opposite to the right angle is the hypotenuse, which is the longest side of the right triangle. Trigonometric ratios are simply the ratios of any two of these three sides. We define 6 core ratios: sine, cosine, tangent, cosecant, secant, and cotangent. Sine theta is opposite over hypotenuse, cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. These ratios form the baseline coordinate functions of all circular calculations. A critical question in geometry is, do trigonometric ratios change if the size of the triangle changes? Let us prove rigorously that they do not. Imagine two nested right-angled triangles, triangle ABC and triangle ABC', which share the exact same vertex A and acute angle theta at A. Because both triangles are right-angled, angle B equals angle B', which are both 90 degrees. Furthermore, angle A is common to both triangles. Therefore, by the angle, or AA, similarity criterion, the smaller triangle ABC is perfectly similar to the larger triangle ABC'. In similar triangles, the ratios of corresponding sides are strictly equal. This means that the ratio of BC to AC is exactly equal to the ratio of B'C' to A'C', which is the sine of theta. This simple but profound similarity proof shows that trigonometric ratios depend strictly on the angle theta and remain completely independent of the physical scale or size of the triangle. Let us geometrically derive the exact values of trigonometric ratios for a standard 45-degree angle. Consider a right-angled isosceles triangle, triangle ABC, where the acute angle at vertex A is 45 degrees. Because the angles of a triangle sum to 180 degrees, the angle at vertex C must also be 45 degrees. Since two angles are equal, the opposite sides must be equal in length. Let us assign the base AB and the perpendicular BC a length of 1 unit. Using the Pythagorean theorem, the hypotenuse AC squared equals 1 squared plus 1 squared, which equals 2. Therefore, the hypotenuse AC has a length of square root of 2 units. Now, applying our definitions, sine 45 degrees is opposite over hypotenuse, which is 1 over square root of 2. Cosine 45 degrees is adjacent over hypotenuse, which is also 1 over square root of 2. Tangent 45 degrees is opposite over adjacent, which is exactly 1. We now derive the exact trigonometric values for 30-degree and 60-degree angles using an elegant geometric construction. Let us start with an equilateral triangle, triangle ABC, where all three sides are equal to 2 units, and all interior angles are 60 degrees. Let us draw an altitude from vertex C perpendicular to the base AB. This altitude bisects the vertex angle into two 30-degree angles, and bisects the base into two equal segments of 1 unit each, creating a 30-60-90 right-angled triangle. By the Pythagorean theorem, the altitude height equals the square root of 2 squared minus 1 squared, which is the square root of 3. Now, choosing the 60-degree angle, the opposite side is square root of 3, base is 1, and hypotenuse is 2. Thus, sine 60 degrees is square root of 3 over 2, and cosine 60 degrees is 1/2. Switching to the 30-degree angle, opposite is 1, and base is square root of 3. Thus, sine 30 degrees is 1/2, and cosine 30 degrees is square root of 3 over 2. Let us understand the behavior of trigonometric ratios as the angle theta decreases and approaches 0 degrees. Imagine a right-angled triangle ABC where we slowly decrease the acute angle theta at vertex A. As theta shrinks closer and closer to 0 degrees, the height of the opposite side BC also shrinks, collapsing towards a length of 0. Simultaneously, the hypotenuse AC rotates downwards, flattening out until its length perfectly matches the base segment AB. In this limiting boundary state, the opposite side becomes 0, and the adjacent side and hypotenuse become equal in length. Applying our ratio formulas to this motivated 0-degree state, sine 0 degrees is opposite over hypotenuse, which is 0 over hypotenuse, or exactly 0. Cosine 0 degrees is adjacent over hypotenuse, which is adjacent over adjacent, or exactly 1. Tangent 0 degrees is opposite over adjacent, which is 0 over adjacent, or exactly 0. Now let us examine the opposite limiting case as the acute angle theta increases and approaches 90 degrees. Imagine a right-angled triangle ABC where we rotate the hypotenuse upwards, increasing the angle theta at vertex A closer and closer to 90 degrees. As the angle grows, vertex A moves closer and closer to vertex B. Consequently, the length of the base segment AB shrinks, collapsing towards a length of 0. At the same time, the hypotenuse AC stands nearly vertical, and its length approaches the exact height of the opposite side BC. In this 90-degree limiting boundary, the adjacent side becomes 0, and the opposite side and hypotenuse become equal. Applying our ratio formulas, sine 90 degrees is opposite over hypotenuse, which is opposite over opposite, or exactly 1. Cosine 90 degrees is adjacent over hypotenuse, which is 0 over hypotenuse, or exactly 0. Tangent 90 degrees is opposite over adjacent, which is opposite over 0, representing division by 0, which is mathematically undefined. Let us master the powerful mathematical relationships that link our 6 trigonometric ratios. Every trigonometric ratio has a direct reciprocal counterpart. Cosecant, secant, and cotangent are defined as the multiplicative inverses of sine, cosine, and tangent. Since sine theta is opposite over hypotenuse, its reciprocal is cosecant theta, which is hypotenuse over opposite. This gives us the fundamental identity: cosecant theta equals 1 over sine theta. Similarly, since cosine theta is adjacent over hypotenuse, its reciprocal is secant theta, which is hypotenuse over adjacent, yielding secant theta equals 1 over cosine theta. Finally, tangent theta is opposite over adjacent, and its reciprocal is cotangent theta, which is adjacent over opposite, yielding cotangent theta equals 1 over tangent theta. These reciprocal equations allow mathematicians and developers to simplify complex algebraic expressions and solve coordinate equations rapidly. We now introduce the quotient and Pythagorean identities, which form the algebraic backbone of all circular trigonometry. First, let us divide sine theta by cosine theta. Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. When we divide them, the hypotenuse cancels out, leaving opposite over adjacent, which is exactly tangent theta. This gives us the quotient identity. Tangent theta equals sine theta over cosine theta. Consequently, its reciprocal cotangent theta equals cosine theta over sine theta. Next, let us apply the Pythagorean theorem to our right triangle. Opposite squared plus adjacent squared equals hypotenuse squared. Dividing this entire equation by hypotenuse squared yields opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared equals 1. Since opposite over hypotenuse is sine and adjacent over hypotenuse is cosine, we derive the classic Pythagorean identity, sin² plus cosine² equals 1. This identity is used by physicists and graphics programmers to calculate wave components and circular coordinates. Let us consolidate our knowledge and review the entire system of introductory trigonometry on our academic dashboard. We have mastered the definitions of the 6 trigonometric ratios, sine, cosine, tangent, cosecant, secant, and cotangent, and prove that they are scale-invariant functions depending strictly on angle theta. We geometrically derive the standard values. For 45 degrees, sine and cosine are 1 over root 2, and tangent is 1. For 30 degrees, sine is 1/2 and cosine is root 3 over 2, while for 60 degrees, sine is root 3 over 2 and cosine is 1/2. We motivated the limiting values at 0 degrees and 90 degrees and established the reciprocal and quotient relations. Finally, we proved the foundational Pythagorean identity, sin² plus cosine² equals 1. Tracing this dashboard, see how these formulas connect in perfect mathematical harmony to model waves, circles, rotations, and vector forces in our physical world. Thank you for attending this comprehensive mathematics lecture on Unit 5, Introduction to Trigonometry. We hope this detailed geometric journey has given you a profound understanding of right-angled triangle ratios, similar triangle scale invariants, standard angle derivations, and core Pythagorean identities. If you found this video helpful, please consider supporting our educational mission by liking, subscribing, and sharing this channel with your fellow classmates. Leave a comment below if you have any questions about standard values, limiting case motivations, or trigonometric proofs. Stay tuned for our next academic lecture, where we will apply these trigonometric foundations to master the applications of trigonometry, including angles of elevation, angles of depression, and calculating real-world heights and distances. Keep exploring the beauty of geometry, and we will see you in the next lecture.